Hello, everyone, and welcome to this session where we dive into the fascinating world of quantum mechanics. Today, we're tackling a fundamental problem, an electron confined within a one-dimensional box. This simple model, known as the particle in a box, is incredibly powerful because it helps us understand how energy becomes quantized, which is crucial for phenomena like quantum dots and even the behavior of electrons in materials. Let's begin by visualizing our setup. Step 1. The diagram. Imagine a perfectly straight line representing our one-dimensional box. At one end, say x equals 0, we have an infinitely high potential wall. And at the other end, x equals L, which is 0.1 nanometers in our case, another infinitely high wall. The electron is trapped inside, bouncing back and forth, unable to escape. Outside the box, the potential energy is infinite, meaning the electron cannot exist there. Inside, the potential energy is 0, allowing the electron to move freely. Step 2. Key variables and constants. To solve this, we need a few key pieces of information. L, the length of our box, given as 0.1 nanometers. Remember, a nanometer is 1/1000th of a meter. So L equals 0.1 times 10 to the negative 9 meters, or 1 times 10 to the negative 10 meters. Me, the mass of the electron, a fundamental constant, approximately 9.109 times 10 to the negative 31 kilograms. H, Planck's constant, another fundamental constant, approximately 6.626 times 10 to the negative 34 joule seconds. This constant is central to all quantum mechanics. N, this is our principal quantum number. It's a positive integer, n equals 1, 2, 3, and so on, and it tells us which energy state the electron is in. En, the energy of the electron in the nth state, which is what we need to calculate. Finally, we need to convert our energies to electron volts, or eV. Because these are very small energies, an eV is a much more convenient unit for atomic and subatomic scales. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. Step 3. Relevant equations and principles. The particle in a box assumes the electron behaves like a wave, and its energy is quantized, meaning it can only exist at specific discrete energy levels. The equation for these allowed energy levels is derived from solving the Schrödinger equation for this specific potential. En equals n squared h squared over 8 mel squared. Here, En is the energy of the nth state. Notice how n is squared, meaning energy increases rapidly for higher states. The h squared term comes from Planck's constant. Me is the electron mass, and L is the box length. The 8 is a constant derived from the quantum mechanical solution. Step 4. Calculation of energies. Let's plug in our known values. First, we'll calculate the ground state energy, which is when n equals 1. L equals 1 times 10 to the negative meters. H equals 6.626 times 10 to the negative 34 joule seconds. Me, 9.109 times 10 to the negative 31 kilograms. Substituting these into our formula for n equals 1. E1 equals 1 squared times 6.626 times 10 to the negative 34 over 8 times 9.109 times 10 to the negative 31 kilograms times 1 times 10 to the negative 10 meters. Performing this calculation, we get E1 in joules. E1 equals 6.025 times 10 to the negative 18 joules. Now, let's convert this to electron volts. E1 equals 6.025 times 10 to the negative 18 over 1.602 times 10 to the negative 19 joules. E1, approximately 3.76 electron volts. This is our ground state energy. For the next 4 lowest energy states, we'll simply substitute n equals 2, 3, 4, and 5 into the same formula. Since En is proportional to n squared, we can simply multiply our ground state energy by n squared. For n equals 2, E2 equals 2 squared times E1 equals 4 times 3.76 EV equals 15.04 EV. For n equals 3, E3 equals 3 squared times E1 equals 9 times 3.76 EV equals 33.85 EV. For n equals 4, E4 equals 4 squared times E1 equals 16 times 3.76 EV equals 60.17 EV. For n equals 5, E5 equals 5 squared times E1 equals 25 times 3.76 EV equals 94.02 EV. So, the ground state energy is 3.76 EV, and the next four lowest energy states are 15.04 EV, 33.85 EV, 60.17 EV, and 94.02 EV. Step 5. Checking our answer. Let's quickly check for consistency. Are the units correct? Yes, we ended up with electron volts, which is a standard energy unit for quantum systems. Does the trend make sense? The energies are increasing as n increases, and they are increasing by n squared, which matches our formula. This gives us confidence in our results. Step 6. Conclusion and applications. What have we learned? The electron inside our nanoscale box can only possess specific, discrete energy values. This is quantum mechanical quantization in action. This model is fundamental to understanding quantum dots, which are semiconductor nanocrystals whose electronic properties are determined by their size and confinement, much like our electron in a box. It's also used to explain the behavior of electrons in metals and semiconductors. Step 7. Additional insights. A crucial insight here is that n cannot be 0. If n were 0, the energy would be 0, meaning the electron would be perfectly at rest. However, due to the Heisenberg uncertainty principle, an electron confined to a small space cannot have both a perfectly known position and a perfectly known momentum, and thus energy. This minimum non-zero energy for n equals 1 is called the zero-point energy, and it means even at absolute zero temperature, the electron still possesses some kinetic energy. Also, notice that as the box length L increases, the energy levels become closer together. For macroscopic boxes, the energy levels are so close they appear continuous, which is why we don't observe quantization in our everyday classical world. Step 8. Final summary. So, we've successfully calculated the lowest energy states for an electron in a one-dimensional box. This problem beautifully illustrates the concept of energy quantization, a cornerstone of quantum mechanics. It shows us that particles, when confined, behave like waves, and their properties become discrete. This foundational model links directly to wave-particle duality and serves as a stepping stone for understanding more complex quantum systems in solid-state physics, chemistry, and nanotechnology. Thank you for joining me today. If you found this explanation helpful, please consider liking this video, subscribing to the channel for more physics and math content, and sharing it with your friends. Do you have any questions or comments? Feel free to leave them below. And if there's a specific problem you'd like to see solved in a future video, you can support the channel through donations. Each month, we'll select a few of your suggested problems to break down in detail.